Okay, so having discussed the philosophy behind the definition of signals and its mathematical representation, and having also discussed the different types of operations on signals, uh, the time domain operation and the amplitude domain operation, assuming that the signal that we are dealing with is basically a function of time. Now today we will move to the classification of the signals and some examples of popularly used signals in the field of electronic circuits. So to start with, let us consider the classification of the signal, right? Classification. So there are different means by means of which we can classify the signals. There are different parameters based on which we can classify the signals. So to start with, let us consider. Henceforth, I will assume that all the signals that we discussed in this course is essentially a function of time. But last day I have categorically mentioned that signal can be function of anything. Signal can be function of any independent parameter. Signal can be treated as a mapping from one domain to another codomain, right? And the elements in the domain can be anything, any parameter. Can be time, can be space, can be both time and space, can be any other parameters. Right? Can be temperature, can be pressure, can be anything. But henceforth we will consider that signal is essentially a function of time, right? So the fundamental signal, something like that, it looks something like that. It's a function of time. We assume this x of t and any arbitrary nature, anything which varies as a function of time. Okay. So this signal, since it is valid, I mean the signal is defined for a particular range of the time, say from t min to t max, and it is defined for all values of time within t min to t max. So this kind of signal, we can consider this kind of signal as a continuous time signal, as you are familiar with. Continuous time signal. That means the signal xt is defined for all values of time within its minimum. Suppose this is my minimum limit of time. This is t minimum, and suppose this is t max. This is t maximum, t max. So the signal is defined for all values of time between t min to t max, for all values, because it's a continuous variation is there. So this type of signal, we will recognize this type of signal as x of t as a continuous time signal. Continuous. So along this horizontal axis, this is basically the independent variable, horizontal axis, and this x of t is defined for all values of this t within this domain, within this particular domain, t min to t max. So t min can go up to minus infinity, t max can go up to plus infinity. So that then we can say that the signal is defined for all values of t, all values of t. So t min can be equal to minus infinity, t max can be equal to plus infinity. So the signal is defined from minus to plus infinity. But particularly I have considered two different values for these two parameters, t min and t max. And if the signal is defined for all values of this time within this range from t min to t max, then it is known as a continuous time signal. Right? Now, what is the counterpart? The counterpart is known as the discrete time signal. So last day I mentioned that when you consider the independent parameters, and if the independent parameters are, suppose for each independent parameter there is a neighborhood, and there is one representative in that particular neighborhood, then it is known as a discrete type of independent parameter, right? So what we are considering is, this is the signal which is defined for all values of time within this t min to t max, and now suppose let me draw the same signal once again. Let me draw the same signal once. I am assuming that even if the signal is defined for all values of t, but we are considering some particular values of time within that range from t min to t max. Suppose this is the first value that we will consider. This is the first value that we will consider. Suppose this is the second value that we will consider. This is the third value that we will consider, and so on and so forth. Time axis is continuous in nature from t min to t max, but for the sake of storing, for the sake of processing, we are not considering all the time instants. Rather, we are considering some discrete time instants. And typically, the difference between two consecutive time instants, typically this difference is also uniform, same. Okay, and suppose this difference is represented as, which is known as the sampling time period, sampling duration, TS. Okay, so the first one, suppose it is taken at, suppose this is the first one, so first one is taken as, say, at TS. Second one at T is equal to TS, at T is equal to, you have taken the first sample, this amplitude, at T equal to TS. Next value of T is equal to 2TS, right? Because the difference is uniform. Then the next, so T is equal to TS, that is equal to your T minimum, right? What is the next value? That is TS plus TS, 2TS. What is the next value? 2TS plus TS, that is 3TS, 4TS, 5TS, 6TS, up to say T max. So now you have finite number of such samples, not infinite samples, because here T max you have infinite number of samples. This is basically a real number set. Now this time you have these samples can be represented as x of, not x of t. Rather, what I can write is, this is basically x of nts, where n is equal to 0, 1, 2, 3, ... Okay, is that one clear? Previously, what we have considered the signal is defined for all values of time, from t min to t max. Suppose t min equal to 0, t max is equal to say 5 milliseconds. So from 0 to 5 milliseconds, the signal is defined for all values of time. Now what we are doing this time we are digitizing, or we are segregating this time axis from 0 to 5 milliseconds. Say the difference is 10 microseconds. Suppose Ts is equal to 10 microseconds. Okay. So if Ts is equal to 10 microseconds, so we have altogether 500 samples. 1 millisecond means 1000 microseconds, right? So if your difference Ts is equal to 10 microseconds, so you have in 1 millisecond you have 100 samples, and in 5 milliseconds you have 500 samples. So previously from this 0 to 5 millisecond, you have like infinite number of samples. This time you have some finite number of samples. So the signal is not defined for all values of time. Signal is defined for some fixed values of time. At t is equal to say 0 millisecond or 0 microsecond, then 10 microsecond, 30 microsecond, 40 microsecond, 50 microsecond, so on and so on. So signal is not defined for 43 microsecond. Signal is not defined for 44 microsecond, or rather signal, you are not considering the value of signal at 44 microsecond, 45 microsecond. Rather at 50 microsecond, then 60 microsecond, 70 microsecond, if the difference Ts is equal to 10 microsecond. So essentially, from the signal itself, what we are getting is a sequence. You will study in detail this particular type of signal in your DSP course in the next year. Okay. So ultimately, what you are getting is not basically x of t, rather x of nts. It's basically a sample set of numbers. Basically, what you are extracting from here is basically that set x of nts. And this is defined for different values of n, 0, 1, 2, 3, 4, 5, and so on and so forth. A set of numbers. And that can be regarded as a discrete time signal. And in DSP language, it is known as the sequence. Now, since Ts is present everywhere, you have 0 into Ts, 1 into Ts, 2 into Ts, 3 into Ts, 4 into Ts, and so on. So basically, this sequence is also represented by x of the third bracket. Typically, this sequence is represented using this third bracket. And for the signal itself, we use the parenthesis. For signal, for continuous time signal, we use this parenthesis. And for sequence, we use this bracket. Okay. So x of n. So ultimately, what you are getting is basically this x of n, set of this x of n, x of 0, x of 1, x of 2, x of 3, x of 4, and so on. Is it okay? Clear? So that is the difference between a continuous time signal and a discrete time signal. So either the signal is continuous, that means the signal is defined for all values of time from t min to t max, or the signal is defined for some fixed values of time. So here, in the codomain set, for a continuous time signal, for the codomain set, you have infinite number of values. Infinite number of values. Because between 0 to 5 milliseconds, you have infinite number of values. Okay. But for the sake of processing, we cannot deal with the infinite number of values. We have to deal with some finite number. You cannot store the infinite number of values. So when you go for discretization, the time axis. So when you discretize the time axis, by virtue of this parameter n, then you have some finite number of samples. 1000, maybe 2000, maybe 5000, that is fixed. Now, if the duration is fixed, suppose t min to t max, that is fixed. Suppose this is 5 milliseconds or 10 milliseconds, and if you reduce this ts, then you have more number of samples. And if you increase this ts, you have less number of samples. And this duration ts is known as the sampling duration or sampling period, and 1 upon this, that means the reciprocal of this sampling duration, is known as the sampling frequency, fs. So sampling frequency fs is known to be the 1 upon ts. That means that if you have higher ts, that signifies lower fs, and vice versa. Fs is known as the sampling rate, and we will discuss this thing in detail in the last unit of this particular course. So how to select these sample numbers and how to select this sampling frequency and all these things we will discuss in detail. That actually creates the prelude of your next subject, that is the DSP in the second year second section. Okay. So that is all about the classification of the signals in terms of the property of the time, whether the time is continuous or whether the time is discrete. If the time is continuous, then we call it a continuous time signal, and if we discretize the time, then we call it a discrete time signal. Even if the time axis is discretized, the amplitude axis is still continuous in nature. Amplitude is still continuous, right? Suppose this signal, this x of t, is having its minimum value as say 0 and maximum value equal to say 2 units. So you can have any value between 0 to 2. The amplitude axis is still continuous, but the time axis is discrete. Okay, so we can also discretize the amplitude axis. That's a different notion altogether. We call it like quantization. So we'll discuss this detail in the last unit of this course. Okay, is that point clear? The continuous time, the difference between the continuous time signal and the discrete time signal. Okay, fine. So now let's move to the second type of classification. After this, then we depending upon the properties of the signal, what we can say, we call a signal depending upon its representation. We call it the even signal and the odd signal. Even and odd signal. There is another type of classification. Even signal and odd signal. I believe that you know what is meant by the even function and odd function. So something like that, almost the same. So we call any signal as an odd signal if any signal xt can be regarded as an odd signal if x of t is equal to minus of x of minus t. For all values of t. That is very important. For all values of t. Over which the signal xt is defined. For all values of t. Then we call it this signal as odd signal. Odd signal. Last week we have discussed what is meant by x of minus t. You know what is x of minus t? That means we just go for time reflection. Take the mirror image along this t equal to 0 axis. Right? Now if x of t is equal to minus of x of minus t, then you call it the signal is odd signal. Right? And on the other hand, if x of t is equal to x of minus t for all t, then we call it as an even signal. Clear? Odd signal and even signal. So for example, if I draw this signal, say let's draw this one, this signal. This is the time axis. X of t, this one. Can you give me an example of an odd signal? Okay. Simple function. Okay. Sine function. Okay. It's great. So let's consider sine function. Okay. I have just drawn only one cycle. One cycle there, another cycle there. Positive cycle, negative cycle. Something like that. The sine signal. I have drawn for only two complete cycles. Only two periods. Right. Now if you measure over there, you see there, this value, this is obtained at t by 4, right? This is obtained at minus t by 4. Just the minus, if you just put a mirror over there at t is equal to 0, this is t is equal to 0 axis. So this value is basically the minus of this value. Right. So sine function is perfect, and it's a perfect example for an odd function or odd signal, sine signal, right? Okay. What about the even function, even signal? Cos function. Apart from sine and cos, I expect you to explore it more. Huh? Yeah, mod function. You know, mod function is not even function. So for mod function, say let it be say t versus x, or you can also consider x versus fx. Doesn't matter. So let it be x, let it be fx. X versus fx. Okay? So mod function, something like that. Mod x right? It's an even function. So if you just take, this is your 0 axis, x is equal to 0. Now if you consider this as your mirror, this as your mirror, if you go in the positive direction, the value, and if you go in the negative direction, the value remain the same. Both the values are same. Okay. So now if this is true for all values of this time, or for all values of the independent variable, for the time I am assuming that time is the independent variable, so that's why I am referring to time. Any doubt? Anyone having any doubt? I am referring to time because I am assuming that time is my independent variable. So it can be true for any, so that's why I have drawn like x versus fx. X can also be your independent variable, right? Now, if this is true for all values of time, or all values of the independent variable, then only I can consider this to be an even function or odd function, depending upon the symmetricity. Right? Now it is also possible that this is not true for all values of time. It's possible. Suppose I am having a signal like this. Suppose I draw a signal like this. This is time, this is xt. Suppose a signal like this. I can have a signal like this, I can always draw a signal like this. Okay. Now you tell me, is it an odd signal or even signal? This signal? Neither or not even. Over a particular period, you may think that okay, it is even function, even signal. Over a particular period. It's not the case always. It's not the case always. But the thing is that any signal, any arbitrary signal can be broken into the even part as well as the odd part. Any arbitrary signal. Even this signal can also be divided into the even part and the odd part. So that's the lemma, that any signal, any arbitrary signal x of t, any signal x of t can be divided, any signal x of t can be divided into its even component plus the odd component. Even component plus the odd component. Any signal, any arbitrary signal can be defined like this. So, had this been the case, then how can I write x of minus t? X of t is equal to x even t plus x of odd t. So how can I write x of minus t? This is basically identity, na? Xt is equal to x even t plus x odd t. So what would x of minus t? So this is basically minus t and x odd minus t. Simple identity. You just replace t with minus t. Now, since x even t is an even function, so x even t is equal to x even minus t. Right? So this is basically x even t. And since x odd t is the odd function, so x odd of minus t is equal to minus of x odd t. So this is basically minus of x odd t. Right? So basically, what you have got x of t. If you know x of t, you can also know what is x of minus t. And from that, you know that x of t is equal to x even t plus x odd t, and x of minus t is equal to x even t minus of x odd t. So you have to find out x even t and x odd t from xt itself. So you have two equations and two unknowns. This is equation number 1. This is equation number 2. Okay? If you add this equation, that will give you 2x even t is equal to xt plus x of minus t, which implies x even t is equal to half xt plus x of minus t. That is even component, even part of the signal itself. What about the odd part? Similarly, you can find out the x odd t is equal to half x of t minus of x of minus t. So any signal can be decomposed. Any signal can be decomposed into its even component as well as its odd component. Any arbitrary signal can be always divided, can be always decomposed into its even and the odd components. Is it alright? Now this definition of a signal being odd. So last day I told you that we start from the very generic concept and then we will go one level higher. Abstraction. This is a very generic concept. So as of now we have assumed that we have a mapping from the real axis to the real axis. But remember last day what we have talked, we have mentioned that signal can be thought as a mapping from the real axis to the complex axis. A real number, a set of real numbers to a set of complex numbers. And any real number can be thought as a subset of the complex number. Right. Now, suppose if your signal x of t is not a real signal, it's a complex signal. Then how this x of, this even signal, odd signal, and whether the signal is even or odd, how are they defined under this condition? And the signal itself is not a real signal. So in that case, we don't call it like even and odd, rather we call it something like that. So if I find that any signal x of t is equal to x complex conjugate minus t, x complex conjugate minus t, that means the signal x of t is not a real signal. It's basically a complex signal. It is having its imaginary part as well as the real part. Now under this condition, if this condition is satisfied, that means x of t is equal to x star of minus t, then we call the signal to be a conjugate symmetric signal. Conjugate symmetric. If this condition holds good, then we call it conjugate symmetric. Conjugate symmetric signal. On the other hand, if I have a signal x of t which is represented by minus of x star minus t, and that has to be for all t, that is also important, that both of these two conditions are true for all t. then it is known as conjugate antisymmetric. Conjugate antisymmetric signal. One is known as the conjugate symmetric, second one is known as the conjugate antisymmetric. Now, if the signal itself is a real signal, then conjugate symmetricity is basically the evenness of the signal, and conjugate antisymmetricity is basically the oddness of the signal. Right? If the signal is a real signal, but if the signal is not a real, so you know that for real signal x of star t is equal to x of t. For real signal, star means complex conjugate is the same thing, no? So x of star of minus t is equal to basically x of minus t. So if the signal is a real signal, then x of t is equal to x of minus t under this conjugate symmetricity condition. That means the signal is an even signal. So conjugate symmetricity for a real signal, conjugate symmetricity implies the evenness of the signal, and conjugate antisymmetricity implies the oddness of the signal. If the signal is a real signal, if not, if the signal is not a real signal, if the signal is a complex signal, then instead of defining the oddness and the evenness in a signal, we have to define the conjugate symmetricity and the conjugate antisymmetricity. Clear? Okay, fine. So we have discussed two different metrics for classification. One is the along this time axis, whether the time is continuous or discrete. So we have a continuous time signal, discrete time signal, then the even signal and the odd signal. Right. Now let's move to the third type of classification, number 3. So the third classification is based on, say, so we have discussed the first one, continuous time, discrete time. Second one is the odd signal, even signal. Then what we have is, suppose I am having a signal x of t over there, right? This signal x of t is there, and suppose let's assume this signal is basically a voltage signal. So let's consider it's a voltage signal. So therefore, if this signal x of t, say, let it be a voltage signal there as a function of time, then if this signal is available across a register, something like that, whose value equal to, say, suppose you have this A, this B, these are the terminals, and between them the applied signal is or available signal is this signal xt, and this is a resistance value, right? Then the question is that what is the power dissipated? How can you measure the power dissipated? Either I square r or d square by r, right? So if x is a voltage signal, then the power is p value. What is the p value? Under this condition, x squared t by r, if x is a voltage signal. On the other hand, if xt is a current signal, if xt is a current signal, suppose xt is a current signal which is flowing through the same register, current signal. If it's a current signal, then the value of this power, this is basically I square r, right? So then I can write x squared t into r. So in one case you have x squared t by r, in other case you have x squared t into r. Now if r is equal to, suppose the unit of, the value of r is equal to 1 unit. So in that case, you have whether it's a voltage signal or the current signal, irrespective of the type of the signal, the power is always here. You find out that the power is proportional to x squared t. That is true. Power is proportional to the square of the signal value. But if r is equal to 1 in that case, this power value is exactly equal to, irrespective of whether you consider current signal or voltage signal, the power is always given by x squared t for a 1 ohm resistance if the value of r is equal to 1 unit, right? So typically what we define how to find out the power of any signal, the instantaneous power. This is not the instantaneous power at time t. Remember, all the like it's the p of t. It's a function of time. It's not the complete total power. It's basically the function that at any particular time, what is the power getting dissipated. How to calculate? You just measure what is the voltage value at that particular time, square it, and you divide it by the resistance. You measure the current at this particular time, square it, and multiply the resistance. Like the resistance is equal to 1, then the power value is basically exactly equal to the square of the signal value, right? So it is customary to use the power as a square of the signal. That's the instantaneous power. Now, how to find out this instantaneous power? Then from the instantaneous power, how can you find out the energy being dissipated? How to find out the energy?
P dot dt. P dot dt.
Yeah. So suppose the signal is defined for all time, from minus to plus infinity. Signal is defined from minus to plus infinity, right? Then under this condition, the energy, if the signal is defined for all t, suppose you have a sinusoidal signal is defined for all t from minus to plus infinity, then the energy E is basically you have to find out the power, the instantaneous power, and then you have to integrate it for all time, right? So you have this one, x squared t dt, and you need to integrate from minus to plus infinity if the signal is defined for all values of the time. If the signal is defined for all values of the time. Okay. Now there is a problem associated with this kind of representation. Can you identify the problem?
Constant of
Huh?
constant of.
Which one?
Say, we are directly proportional to an R or R is equal to 1.
Yeah, we have assumed that R is equal to 1. So x squared t dt is basically what? X squared is basically the power, instantaneous power at time t, at time delta t. What is the power dissipated is x squared t. So if you multiply this with the time dt amount, that will give you the energy at that particular time. You have to add all these things. So integration from minus to plus infinity x squared t dt. Now the problem is that if the signal is defined for all values of the time, for example, let's consider a sinusoidal signal. A sinusoidal signal which is defined for all values of the time. Now if you compute this integration, right, then what will be the value? After integration, what will you get? After it is 0. You integrate from minus to plus. Suppose you integrate a single cycle. You integrate a single cycle of sinusoid. We have already studied about this mean square and root mean square. All these things you have studied also. You studied hopefully. Or if not, so you are studying at this particular semester in electronic circuits. You are studying, right? They integrate a sinusoidal signal and if square and integrate something like that. So it will give you some value, and then you are repeating for all such the entire cycle from minus to plus infinity. And there is a particular property associated with the sinusoid. I am coming to that. So that value ultimately after this integration, the value will not converge. That will go towards infinity. Right? So energy is becoming infinite. Or this kind of signal is defined for all values of time, and you have like you don't have any decay component. If every for example, you find that okay, if you integrate from minus to plus infinity, basically you can segregate them, and the total value is becoming infinite. So under this condition, how can you define the average power of this kind of thing? Average power
divided by.
If you find out this integration is equal to infinite, if you divide it by something, so once again it will be infinite.
For one single cycle. For a single cycle.
Yes, for a single cycle. So in that case, what you need to do is that you find out that this energy is equal to something minus 2 plus x square dt, and that is becoming infinite, very large. So there are a few types of signals. For which the definition of the energy is not sufficient. Definition is not sufficient at all. And based on that, what we can do, we can also classify the signals from different perspective. I'm coming to that, leaving this slide right at this moment. I'm coming to that once again. I'll refer back to this slide once again. So you understand what is the problem associated with this. If you integrate this one, say let's consider, because you are pretty much familiar with the sinusoidal signal, and if you just find out this, x square t sine square omega t, or a sine square a sine omega t whole square dt, and if you integrate for all values of t from minus to plus infinity, this integration level converges. Because you know the sinusoidal signal will repeat itself. So based on that, you have another definition, the classification mechanism for the signal itself, based on the periodicity of the signal. Right. So this is known as, a signal x of t is known to be a periodic signal if x of t is equal to x of t plus t for all values of small t and some values for capital T. If this condition holds good, that means x of small t is equal to x of small t plus capital T for all values of t and for some fixed values of capital T.
So it will be some values or unique value of capital T, because capital T should be the least.
Okay, I'm coming to that. Yeah, this question is very much pertinent. I'm coming to that. Now the minimum value of t for which this condition holds good, this is known to be the fundamental period of the signal. Fundamental period. So suppose let's consider, as I mentioned that this condition holds good, that okay, I have written something, na, x of t is equal to x of t plus capital T, but the condition is very important. You know the Ohm's law. But there are some conditions, preconditions for the Ohm's law. You have Charles' law, Boyle's law. So there are some preconditions. The condition has to be mentioned properly. Here also, I cannot say like x of t is equal to x of t plus capital T. And if I leave it at this particular point, and if I say that okay, the signal is a periodic signal, then doesn't have any sense. You have to complete the sentence. X of t is equal to x of t plus capital T for all t, for all small t, and for some values for capital T. Now the minimum value of the capital T for which this condition holds good is known as the fundamental period. Right? And suppose this value is equal to T0. So what I can write, x of t is equal to, as I mentioned, this is true for some values of capital T. So these values are, you can arrange them in the ascending or descending order. Ascending order you can arrange them. So x of t plus T0. Is it alright? X of t is equal to x of t plus T0. So T0 is the minimum value of this capital T for which this condition holds good. Now if it is true for T0, it is also true for 2T0.
Yes.
3T0, 4T0, 5T0. So T0 is basically the fundamental period. T0 is a fundamental. For example, if I consider the signal x of t is equal to a sine omega naught t plus phi naught. Suppose the signal is defined like this. It's basically a sinusoidal signal. X of t is equal to a sine omega naught t, that's a capital omega naught t plus phi naught. Okay. Now I can write x of t plus capital T. What is that? This is basically a sine omega naught t plus capital T plus phi naught, right? And you know what is this omega naught? What is this omega naught? Omega naught is basically the angular frequency. This angular frequency is given by 2 pi by T naught, or 2 pi into F naught. F naught is the Hertz frequency and 2 pi F naught is the angular frequency. 2 pi F naught. Right. So now if you just plug in the values, then you will see that once again you are getting, you have to put T equal T naught there. Then you are getting x of t once again. So the signal of the sinusoidal signal, for example, a sine omega naught t plus phi naught or a cos omega naught t plus phi naught, they are inherently known to be a periodic signal. They repeat itself after a certain period. And the minimum value of this t, minimum value, because you can consider, okay, that might get repeated after say 2 t naught, 3 t naught, 4 t naught, 5 t naught, the minimum value of this t naught is known as, or minimum value of this t is known as a t naught, the fundamental period. Okay. So a sinusoidal signal, as I mentioned, a sinusoidal signal, a continuous time sinusoidal signal is always a periodic signal. And it is defined, say, from either you can define it from 0 to capital T, or you can also define it from minus t to capital plus minus t by 2 to plus t by 2. I will define it from 0 to capital T, 0 to capital T naught, or you define it from the minus t by 2 to plus t by 2, minus t naught by 2 to plus t naught by 2. One complete full. Okay. But the situation is not that easy for a discrete time signal. Discrete time sinusoidal. So let me consider how can we write down the expression for the discrete time sinusoidal signal. So we know that this x of t is given by, say, a naught sine of 2 pi f naught t plus phi naught. This is defined a sinusoidal signal 2 pi f naught t plus phi naught, where f naught is given by 1 upon t naught. Okay. Now, when you sample the signal, now this is a discontinuous time sinusoidal signal. This is defined for all t, something like that. So you have t there. This is x of t. Now, if let's assume that phi naught is equal to 0, so then one cycle looks something like that. Okay. So this signal is defined for, it's a continuous time signal. And it's a periodic signal, as you know. Continuous time signal, periodic signal. So after every t or t naught, you have the same thing gets repeated. Now suppose from this signal itself, I would like to have the samples. This. As we started our today's discussion with the continuous time signal and the discrete time signal, so let's take those samples. So judiciously, I have drawn those samples. So that it seems that it's a periodic signal, but it is not the case. I am referring why not. Now, if you sample the signal, so then x of nts, what is this x of nts? This x of nts can be represented as a naught sine, I can write 2 pi f naught, and in place of t, what I can write? nts plus some phi naught, right? So that is basically a naught sine. So this is basically what? Omega naught t. This 2 pi f naught is basically omega naught. This omega naught, sorry, not this omega, basically the small omega you have. This omega naught is basically 2 pi f naught. So I can write like a sine omega naught t plus n, or plus phi naught. What about the discrete time counterpart? if you have like a naught sine omega naught t plus phi naught, what will be the discrete time counterpart? A naught sine some omega naught n plus phi naught. In the continuous domain, you have like x of t is equal to a naught sine capital omega naught t plus phi naught. The discrete equivalent is a naught sine small omega naught n plus phi naught. Right? So now try to find out the relationship between this capital omega naught and the small omega. What is this small omega naught? So this small omega naught is how much? 2 pi f naught into Ts. So what is this Ts? 2 pi f naught. Ts, you know, Ts is equal to basically sampling duration. So Ts can be represented as f naught is equal to T naught. That is one thing. F naught is equal to T naught. That is associated with the signal itself. Right? And Fs is different thing. Fs is equal to 1 by Ts. Okay. So 2 pi f naught by Fs. Now if this ratio 2 pi f naught by Fs, if it's a rational factor of 2 pi, that means this f naught by Fs can be represented as p by q form, in the p by q form, where q is not equal to 0. Then only I can say that, okay, this signal, this x of nts, will be repeated after a given n. So this one, so x of n can be considered to be a periodic signal if x of n is equal to x of n plus some capital N. Yeah, you get my point. For continuous time signal, a signal is not to be periodic if x of t is equal to x of small t is equal to x of small t plus capital T. But in the discrete equivalent, you don't have any notion for t, rather you have the notion for n, the index, the 0, 1, 2, 3, 4 index. Right? Suppose I have a sequence something like that. I have a sequence like this. 1, 2, 3, then 1, 2, 3, then 1, 2, 3, and so on. So I can call this sequence as a periodic sequence with a period equal to how much? 3. I can have a sequence like -1, 0, 4, 2, -1, 0, 4, 2. This is a periodic sequence with period 4. So you have to find out that whether the signal gets repeated, yes or no, for all values of t or for all values of n, and what is the frequency of repetition. After how many samples the signal gets repeated. So in the first case, you have after every 3 samples you have the same value. In the next case, after every 4 samples you have the same value. So here also, so therefore what I can write, so x of n is equal to x of n plus capital N. Okay. So had this been the case, now what was our definition? X of n is equal to something like a naught sine omega naught n plus phi naught. Okay, where omega naught, this frequency is given by 2 pi f naught by fs. Here, so suppose I have to understand whether the signal is periodic or not. Periodic signal or periodic signal. So I have to find out x of n plus capital N. That will be a naught sine omega naught n plus capital N plus phi naught. Okay. This is basically A naught sine. I can write omega naught n plus phi naught plus omega naught capital N. Okay, so what is this omega naught capital N? So omega naught capital N is equal to 2 pi f naught by fs into capital N. So capital N, you understand that, okay, capital N is always a positive integer, non-zero positive integer. Okay, now if this can be represented as, so you know that A sine omega naught n plus 2 pi. So sinusoidal signal is something which gets repeated after every 2 pi radian, right? So A sine alpha and A sine alpha plus 2 pi is equal to the same. So A sine, so forget about A, only some, right, like sine alpha plus 2 pi or rather 2m pi is equal to sine alpha. That is the case for any value of m, 0, 1, 2, 3, 4 like that. But m has to be an integer. Remember, m has to be an integer. M cannot be a fraction. Is it okay? Sine of alpha is equal to sine alpha plus 2m pi. So here, if this omega naught n, this one, if this can be represented as 2m pi, then only you can say that. So what about then? If this is 2m pi, that means what? You equate this one. What we are getting? 2 pi to pi gets cancelled. So f naught n by fs has to be equal to sum m. Right? Or as I have told you, f naught by fs. That means that what is f naught? F naught is the heart frequency of the signal. What is fs? Fs is the sampling rate of the discrete signal. If that can be represented in this m by n form, in the rational form, where n is non-zero, capital N is non-zero. Now, if this condition gets satisfied, then only you can say that, okay, the discrete signal is also periodic in nature. Can you get the point? If this condition is not satisfied, then the signal is your original signal, is your continuous signal, is a periodic signal. But if you sample the signal in an erroneous fashion, right, then the signal is not at all, the discrete signal is not at all periodic. I can give some example. So you have got this signal. This is a signal, or let's draw one more cycle that will be easier to understand. Let me go to the next. So this is t, this is x of t. This signal is a periodic one, but the samples that you are taking, like this, then this, then this, then this. Like this. Do you find any similarity between the first half cycle and the third half cycle? This first half cycle and third half cycle, no. Because I have taken the sample in an erroneous fashion, I have not maintained that particular formula, that this f naught by fs is equal to m by n form. Then it is not possible. So even if the original signal is a sinusoidal signal, that x of t a naught sin omega naught t plus phi naught, even if it is continuous and periodic, but its discrete version is not. Clear? Which one?
Last one is
So here you see that this sample. So here I have considered, suppose let's take some particular value, right? Let's call, say, f naught is equal to, let's take some value, say 10 hertz. Let's take f naught is equal to 10 hertz, right? And suppose you take fs. If you take fs is equal to, say, let's call any number, irrational number. You take any irrational number for that. That cannot be represented in this particular form. That means f naught by fs. I cannot write f naught by fs. I cannot write in this form, m by n form. So in that case, what I find? What is fs? Fs is the duration. Fs is the, or 1 upon fs is the duration between these two consecutive samples. Now, if your fs value, suppose let's consider fs is equal to, let's consider 3 pi. Okay. No, not take this one. Yeah. How many samples you have considered? Within one cycle, suppose your time t or t naught is equal to 1 millisecond. Okay, so you have to ensure that within this 1 millisecond, you have from 0 to 1 millisecond, you have some fixed number of samples. Might be 10 samples, might be 20 samples, might be 50 samples, might be 40 samples. So this Ts can be represented as this Ts or T naught is equal to 1 millisecond, and you take, say, k number of samples in one period, in one full period. Okay, k number of samples in one full period. So therefore, what will be the Ts value? Total duration is T naught, and you take full k number of samples, right? Then what will be the Ts? T naught by k. So the first sample will be taken at 0, next sample will be taken at T naught by k, next one will be 2 T naught by k, 3 T naught by k, 4 T naught by k, and then ultimately k T naught by k, that means at T naught. So one cycle is over, then you go to the next cycle, so the same values are repeated once again. So here the 0th value and here the 0th value, here the first value, second value, they are matched. They match with each other. But so this is only possible if this entire duration is divided accordingly. If not, if they are not divided accordingly, that means suppose let's consider that, okay, T naught can be say So 0.95 millisecond, right? T naught is equal to 0.95 millisecond, and you take Ts to be, say, 0.07 millisecond. So in that case, 0.95 millisecond, 0.07 millisecond. So the first sample 7, 0.07 millisecond means how much? 70 microsecond. 1, 2, 3, 70 microsecond. So 70 microsecond, 140 microsecond. In this way, you cannot complete this entire cycle altogether. In the first period and the first sample in the next period are not the same. So that means this sample here, and the sample here are not the same. This is only possible if you maintain this particular formula. That means this F naught by Fs is represented in the M by A. Okay. So that is all about the periodicity. Now let's move to this one. Yeah. Now suppose you have some signal, say for example a sinusoidal signal, which is basically a periodic signal. Right. Now if it's a periodic signal, now if you measure the power content, instantaneous power, that is fine. Now if you measure the energy of that particular signal, that energy becomes infinite. If you integrate a sinusoidal signal, you square it and if you integrate it, then it will give you infinity, the value is equal to infinity. Then how can you define the energy content? So obviously for this kind of signal, which is defined for all time and it's a periodic signal, so you cannot define the energy content. For which there is another alternative definition is there, and that definition is known as the average power. This average power P average, over a period, single period, is represented as, how can you find out the average power? You need to find out the total energy in a single period. So let it be say minus T by 2 to plus T by 2, x square T. That's the total energy within a single period, and you divide this by the total time, 1 by 2. That will give you the average power. Average power. Any doubt? Now this will give you a finite one. Even if your energy is infinite, for a sinusoidal signal, for example, but this P average, 1 upon T integration over minus T by 2 plus T by x square T dt, that is finite. So there are some signals for which the energy definition, if you go by the energy definition, that will give you some infinite value. But if you go by the power definition, that will give you some finite value. And these signals are known as the power signals, for whom the energy is infinite, but average power is fixed, or average power is finite. One perfect example is the sinusoidal signal. Energy is infinite. If you calculate the energy, total energy of any sinusoidal signal, if you integrate from minus to plus infinity, this integration will never converge. This will diverge to infinity. So there should be some alternative definition for this type of signal, for whom the energy content cannot be defined properly. And this alternative definition is the power definition, average power definition. You just measure the total energy in a single period, and then you divide this by the time duration. Okay, and the signal for which the energy is finite, these signals are known as the energy signal. That means the signals which are not defined for all values of the time. I will give you an example. There are certain signals which are not defined for all values of time. For them, you can easily measure the corresponding energy, and that energy will be a finite one. Okay, so there are two different types of signals on the basis of the energy content. One is the energy signal, for whom the total energy is fixed or finite. Okay, these signals are known as the energy signals. And there are certain signals for whom the total energy is infinite, so that's why you require an alternative definitions for energy. And that is in the form of the average power. And this average power will be finite. Even if the energy is infinite, but the average power will be finite, and that is defined by 1 upon T integration over minus T by 2 to plus T by 2 x square T dt. Similarly, in the discrete domain, you can have the equivalent representation. For the discrete domain, this energy E is represented by, instead of integration, you have the summation x squared n for all n. That is the definition. For all n, you have to find out the square of this and you have to add them up. That is the energy definition. And similarly, for the power, the average power definition is something like that, like 1 upon n integration summation n is small n is equal to 0 to n minus 1 x square n. That is for the discrete time counterpart. And even if the signal is not a real signal, so in that case you cannot write like x square n or x square t. In that case, what you need to do is that mod of x square t or mod of x square. Mod x n, mod of x n square, mod of x t square. You have to put the mod sign there. If the signal is not a real signal, if the signal is an imaginary, it's a complex signal kind of thing, a plus jb in this particular form. In that case, you cannot write like x square because energy and power cannot be imaginary numbers. You have to write a mod of x t, mod of x t square, mod of x n square. Okay. So this definition of this energy signal and power signal, they have certain correlation with the periodicity of the signal. If any signal is a periodic signal, for them, you cannot define the energy. So periodic signal is always a power signal. Periodic signal is always a power signal. Okay. Okay. So now let's move to the another type of signal, or rather domain of signals. One is known as, hopefully you have heard about this type of signals. One is known as a deterministic signal. Second one is known as the random signal. One is known as a deterministic signal. That means for every time you can represent the signal in mathematical form. So I can represent a deterministic signal by finite number of elements. Say I am having x of t, so I can represent anything. Say a naught cosinusoidal 2 pi f naught t plus phi naught. This is known as a deterministic signal. Why deterministic? Because at any point of time, if the other parameters are given to you, f naught, t, phi naught, if the values are given to a naught, if these values are given to you, then you can very easily calculate the signal value at any particular time instant. So deterministically you can calculate the sample value, signal value at any point of time. That's why it is known as a deterministic signal. It can be sinusoidal, it can be other type of signal. However, there are certain signals for which you cannot at any particular time, you cannot deterministically say or deterministically calculate the exact value of the signal. And these signals, they are not a single signal, they form an ensemble. They form an ensemble, and as a whole, they will give you certain characteristics of their set. And these type of signals are known as a random signal. So last day I told you the example for say the market price. Market price at any particular day. What will be the market price for gold, or what will be the market price for say particular Sensex? It is very difficult to predict at a particular point of time. So it is basically you can't say specifically what should be the value. So suppose this is 90,000 today. It can be 92,000 tomorrow, can be 88,000 tomorrow, or can be 86,000. So you cannot predict unless it occurs. Once it occurs, then you understand, okay, this is the value. But you cannot predict. At t is equal to t naught, you cannot predict what will be the value at t is equal to t naught. Or t naught plus delta. It is not possible. It cannot be deterministically defined. The temperature, weather forecast, it's not just possible. You cannot say what will be the temperature after 4 hours, after 5 hours, you don't know. Right now, suppose the temperature is 30 degrees centigrade outside. it can be 31 degrees centigrade. So now it is 130. So after 3 hours, after 2 hours, it can be 31 degree, can be 32 degree, can be 29 degree, can be 28 degree. So you cannot predict it completely. Right. So these signals are known as the random signal, but they have certain features. They come from a process which is known as a random process, and these random and all the signals originated from the random process, they will exhibit a particular feature. They have certain, so okay, now today is the month of March, so you can't say that okay, now until unless this is very absurd, you can't say that the outside temperature will drop down to 8 degrees centigrade. It's not just possible, or it cannot rise to 50 degrees centigrade here in Kolkata. It's not just possible. So you know that okay, it can be within say 28 to 32, within that range, with certain variations, with certain changes. So these signals are not defined properly, but what you can have certain parameters, some statistical parameters, by means of you can define those things. So the outside ambient temperature is a perfect example of a random signal. You can't say what will be the average temperature today. Average, you know how to calculate the average temperature? The way you have calculated this average is very easy. Find out the average at every hour, and then you just take the sum them up and divide them by total number of hours, the total number of samples that you have considered. If you take one sample in every hour, so you have to divide by 24. You will take 2 samples in every hour, then you have to divide it by 48. Measure the temperature and find out the average. Suppose the average temperature today, last 24 hours, suppose this is say 20.3 degrees centigrade. Tomorrow it can be 20.5 degrees centigrade. Yesterday it was say 21.1 degrees centigrade. But you have some fair idea about what can be the temperature. It cannot go to say 40 degrees centigrade. Here in Kolkata in the month of March, it is not just possible. Or even it cannot go to 80 degrees centigrade. It's not Darjeeling, it's not 80 degrees centigrade, right? But you have some fair idea about what should be the minimum and maximum value. Okay, this is the minimum value, minimum can be 18 degree, maximum by 22 degree, and the signal will vary within that, the temperature will vary within that. So these type of signals are not properly defined using some mathematical formula, or at any point of time you cannot just plug in the values and you can predict. Okay, you can predict. Nowadays they are defined as AI/ML models are there, so you can predict the values. But obviously, when you predict the values, there is always some error associated with that. Unlike the deterministic signal, say for example, you have some sinusoidal signal, you have some cosinusoidal signal, you have some other types of signals, right? So you know at any particular x value what will be the effects. It is clearly known to all of us. But this is not possible for some random signals. So market price is the best example. The price of fuel, price of LPG nowadays, petrol price, room temperature, ambient room temperature you can control to some extent, but ambient temperature you cannot control. Right? Humidity you cannot control. You have a clear idea about this, but obviously it is not fixed. So these type of signals are known as random signals. And random signals are generally identified by certain statistical parameters. And there are certain statistical distributions. Hopefully you have studied statistics in mathematics, right? The probability density functions you have studied hopefully. Have you ever heard about this Gaussian probability distribution functions? Yes or no? Gaussian probability distribution function? No, we have not studied. Okay, for example, say the marks obtained by the student in any particular semester. So I can't say what should be the marks. The marks obtained by typically what happens? I know that okay, if the class is fairly they are sincere and all attentive, then I say that okay, the marks can be minimum marks can be say 55, maximum marks can be say 90. Right? But I can't say which students will get which marks. Isn't it? It is not deterministic. I say that okay, the class is okay, it's attentive, so they have attended almost all the classes and they are very sincere. So I guess that okay, the minimum cannot be less than 60 or 65, and maximum say it's up to 90, 95. So that is the range, 55 to 90, 60 to 90. and all of you, all of the students in the class, they can score within that particular within that particular range. And typically, what happens? Typically, all the natural phenomena, for example, all the natural phenomena they follow a particular distribution, and that distribution is known as, I don't know whether you have heard about this or not. That distribution is known as the Gaussian distribution, something like that. A Gaussian distribution. This is x, this is fx. A Gaussian distribution. Suppose this one is say this is 50. Suppose this one is say 90. And this peak is say 70. That is a probability density function. So the minimum cannot be less than 50, maximum cannot be higher than 90, and most of the marks they are clustered around 70. That is known to be the mean value. So they are coming from the random process, and there are different parameters which can control the random process. For example, your marks in the semester examination, there are several parameters. So your preparation, the number of subjects, number of papers, then you have the quality of the question paper, whether it's hard or very easy. The preparation, then your performance in the exam, the marks, the answer scripts are evaluated, right? So all this also they will ultimately control, they will ultimately govern the marks that you will get ultimately in the semester examination. So I can't predict, anybody cannot predict, nobody cannot predict this one. What will be the value? What should be your marks at this particular subject? Even you cannot predict. Right? You cannot predict. It can be 70, can be 72, can be 75, can be 85 also. You can, because there are so many parameters associated with that. So this is basically a random number, or random. The marks that you get in an exam is basically a random number, and that gets generated from a random process. And there are so many influencing parameters which can control this. That is also a signal. Remember, signal is not always a function of time. The mark that you get is also a signal, right? But this is not deterministic. Completely random. There are few parameters based on which this randomness is evaluated, and most of the time we will try to reduce, or few people rather try to reduce the randomness, so that because that is our common practice. Don't go for any randomness. You just try to be very much associated with the fixed ones, right? So anyway, so for this kind of signals, which are random in nature, it's not deterministic in nature, they always obey some probability density function. Even if it is random, but you have some clear idea about the value that you are supposed to get. Right? Any doubt about understanding this one? This random signal and the deterministic signal? Anybody having any doubt? No doubt. So hopefully you have covered the different types of signals, the different classifications on the different types of signals. For example, we have started with the continuous time and the discrete time, then even signal or signal, then periodic aperiodic signal, then from the periodicity and aperiodicity, the energy power signal, right? And then finally the deterministic and the random signal. And remember, these signals, these different types of signals, different classification metrics, they are independent of each other. A continuous time signal can be periodic, can be aperiodic, can be random, can be deterministic, can be odd. Can we get the point? A continuous time signal can be periodic, can be random. Periodicity and randomness, can it come together? Can it come together, periodicity and randomness? Yes or no? No. Suppose sinusoidal signal. It is periodic. Periodic in nature. It can be continuous, can be discrete. If it is sinusoidal, then you know it's an odd signal. If it's a cosinusoidal signal, it should be an even signal. So odd signal can be periodic, even signal can be periodic. Right? So there are different types of. I can ask if you understand the concept very well, then you may be asked, give some examples of some signal which is periodic, continuous, and even. Periodic, discontinuous, discrete, and odd. So periodicity and the continuous type of the nature, continuous type of the signals, and the evenness and the oddness. So they are basically, these different parameters are independent of each other. They have no relation with one another. So with this basic understanding, now let's move to some of the very popular signals. So we have given the, last day we have defined the different operations of the signals, and today we have discussed the different class of signals. Now let's take some of the examples, and then I will ask you to identify in which category they belong. Right. So to start with, we will start with very fundamental signal, like an exponential signal. Hopefully you have all heard about the exponential signal, right? Exponential signal you have heard about? Yes. X of t is equal to, say, a e to the power alpha t. Right? And suppose this is defined for t greater than or equal to 0. Let me sketch the signal first. This is t, this is x of t. How does it vary? Exponential, how? Will it increase or will it decrease? Will it decrease or will it decrease?
Depend on
Yeah, depend on alpha. Suppose I assume that a is a positive quantity. A is a positive quantity. Okay? And suppose let's consider a to be 1. To make it simple, let's consider a to be 1. Okay? Now if alpha is greater than 0, alpha is greater than 0, that means it's an increasing exponential. Like this. And if alpha is less than 0, so this is for alpha. This is for alpha greater than 0. Alpha greater than 0. And for alpha less than 0, obviously it seems that the signal is a continuous time signal, right? There's no doubt. It's continuous. So we'll discuss continuous time signal in this particular course. Okay. What about the periodicity? What about the periodicity? Is it a periodic signal? No, it's not a periodic signal. Is it a deterministic signal or random signal? Deterministic signal. Okay. Then what about the energy content? What about the energy content? How can I find out the average power? Depends on alpha. Yeah. Okay. Fine. This is one thing. Okay. Then let's consider another signal. Sinusoidal signal, all of you know, right? All of you know sinusoidal signal. And here what we have considered, that both this A and alpha. Here we have considered both this A and alpha. They are real. We consider A to be constant real, say 1, and alpha to be real constant. So alpha can be the complex number as well. In that case, if alpha is a complex number, alpha is equal to say a plus jb in this particular form, or b plus c plus jd in this particular form, then the signal xt that you are getting is not a real signal. You have the corresponding real part as well as the imaginary part. Right? Okay, for example, let's consider x of t is equal to a e to the power alpha plus j beta t. A e to the power alpha plus j beta t. So this is basically a e to the power alpha t into e to the power j beta t. Do you know the Euler's formula? E to the power jx means yeah. So a e to the power alpha t, this is a real constant. It's not constant basically, it's function of time, but still cos beta t plus j sin beta t. So if you have, so why I have introduced this one? Later on you'll see that this basically it's a complex exponential signal. Complex exponential signal. And from where you exercise the cos part as well as the sine part. So when I visualize a cosinusoidal signal, this cosinusoidal signal can be visualized, and the cosinusoidal as well as the sinusoidal signals, they can be visualized as the part of a complex exponential signal. When you have some phasor, a complex exponential phasor, when it is rotating at a particular speed, and then the corresponding x coordinate and the y coordinate will be giving you the sinusoidal signal and the sinusoidal signal as a function of time. Right. So that's all about the exponential signal. Now let's move to another signal which is very popular in signals and systems. I don't know whether you have heard about this signal or not. This signal is known as, here you have t, they're giving you the name u of t. This signal is defined only for positive value of t, and this is something like that. This is 1, this is 0. Have you ever heard or have you ever seen this type of signal? It's not signal. It's not signal. So this signal is defined like u of t is equal to 1 for t greater than 0, and this is 0 for t less than 0. And this is undefined, or it's not properly defined at t is equal to 0. There is a discontinuity at t is equal to 0. And that signal is known as a step signal. A staircase kind of signal, step signal. Suppose in your circuit you just attach on battery at t is equal to 0. That means at battery means what? Constant signal, constant voltage. 5 volt battery, 9 volt battery, 12 volt battery, constant signal. So at t is equal to 0, there is a rise, and that rise is a constant. This is known as a step signal, right? For t less than 0, this is 0. For t greater than 0, this is 1. Now you tell me, is this signal even signal? Is it an even signal? Odd signal? No. So you can decompose now odd and even component from this. Can you decompose this one? It's not odd, neither odd nor even. They can decompose two different components. Fine. U of t. What about the energy of this signal? Is it a periodic signal? Is it periodic or aperiodic? Huh? Is it periodic? Huh? Does it repeat itself after certain time? No. Aperiodic. Right? Aperiodic. What about the energy? What about the energy? Will it convert? No. Do not convert. This signal is known as the step signal, and using this signal you can construct different types of signals. And that is considered to be a very basic signal to start with in signals and systems. So you have a particular system, and if the system, so as of now we have not discussed what is system, but you understand what is system all about. Any kind of system, mechanical system, electrical system, any kind of system, chemical system. And with regard to electrical system, suppose you feed the system with a battery, DC battery. That means at t is equal to 0 or t is equal to 0 plus, you have certain voltage, and for t is equal to 0 minus, you don't have any voltage. How does the system respond? That can be easily understood if you analyze the system with this kind of signal. So that's why this kind of signal is playing very important role in signals and systems, and in many other systems like control systems, any other systems. Circuit can have the essence of this particular signal, because that gives you the flavor. Okay, at t is equal to 0 minus, I don't have anything. At t is equal to 0 plus, I apply something, a constant one, right? So this can be a battery, constant battery. So this can be realized by virtue of this type of signal, U of t. This is one of unit step signal. Unit step. Let me write it down. The name, very popular one, unit step. Unit step signal. Now, last day I have told, okay, we have certain operations on the signal, right? On the amplitude axis as well as on the time axis. Okay. Now, amplitude axis we have discussed about addition, multiplication by constant, or can you multiply by another signal, differentiation, integration, right? Now if you integrate this signal, what will you get? If you integrate this signal, U of t. If you integrate this signal, what will you get? Huh? No, if you integrate the signal, yeah, t. This is U of t is equal to 1. So if you integrate integration over U of t, dt, then what will you get? You will be getting a signal like this. This is known as R of t. This R of t is basically integration over minus infinity to t u of tau d tau, and that is defined like this is equal to t for t greater than or equal to 0, and that is equal to 0 for t less than 0. Okay. Now this signal is continuous. Obviously at t is equal to 0, there is no such discontinuity, unlike your this ut signal. This is known as a ramp signal, ramp. This is RT, is known as the ramp signal. So ut is the basic signal, and from ut, if you integrate ut, you will be getting RT, the ramp signal. And on the other hand, if you differentiate RT, you will be getting ut, isn't it? If you differentiate the ramp function, you will be getting the step function. Now the question is, if you differentiate the step function, what will you get? Not 0. That's a very tricky question. What will you get if you differentiate the step function? Differentiation means what? If you have some change, that will be reflected. Differentiation, that is the basic notion of differentiation. If you have any change, that will be reflected. Now here you see that for ramp signal, the change was constant. Over here for t greater than 0, it was increasing at a particular rate. Change was constant, so that was reflected over there, constant change. And there you don't have any change, 0, so 0 over there. Now for the step signal, you have a change at t is equal to 0. At t is equal to 0 minus, you have 0. At t is equal to 0 plus, you have 1. So for very small duration of time, for delta amount of time, you have a certain change, and that will be reflected. Right? Everywhere you have 0. For t greater than 0, this is constant 1, so no change, so 0. T less than 0, everywhere 0, 0. But t 0 minus to 0 plus, there you have a certain change from 0 to 1, a rise from 0 to 1. So therefore, if you differentiate this step function, then what will you get? Then this function is known as, if you differentiate the step function, this function is known as the impulse function. And that function is defined like this: delta t, which is equal to 0 for t not equal to 0. That is obvious. 0 for t not equal to 0. If t is not equal to 0, that is 0, delta function. And whatever the second definition of delta t, so okay, you understand that if t is not equal to 0, that is 0. No big deal. What happens at t is equal to 0? What happens at t is equal to 0? But we cannot define infinity. Huh? Ideally, you can say it's infinity for very small delta. So yeah, how to define infinity once again? The question is, how can I define infinity? Basically, how to visualize this delta function. This is t. Let's define this function x of delta t, right? What is that? X of delta t. Let's consider this pulse. Pulse, you understand? Minus delta by 2 to plus delta by 2, you have this particular nature. Constant. What is the area under this curve? That is unity. Height is 1 by delta and width is delta. We multiply the 1 by delta with delta, that is unity. Okay? So unit area pulse x delta t. Minus delta by 2 plus delta by 2. Height is delta by 2. 1 by delta. Okay? Now, let's assume that your delta value is approaching towards 0. Delta is approaching towards 0. That means 1 by delta will approach towards infinity. And then you can visualize this delta function, delta t, as limit delta tending 0 x delta t. Delta tending 0 x delta t. Okay. And everywhere you find, if you integrate this delta x delta t over a particular period from minus delta by 2 plus delta by 2, that will give you a unity value. So here comes the second definition of delta t, that is equal to minus infinity to plus infinity so that is the second definition, delta t dt, that is equal to unity. Minus to plus infinity, delta t dt is equal to unity. And these two definitions together will give you the basic essence of the delta function. So delta function is defined for, while defining delta function, you have to provide two different definitions. First one is that this is a kind of function which is not defined for any value of t other than 0. It is only defined for t is equal to 0. But the thing is that at t is equal to 0, we cannot define it properly. For defining the signal at t is equal to 0, you have to refer to all the time from minus to plus infinity. So minus to plus infinity, delta t dt is equal to unity. And delta t is equal to 0 for t not equal to 0. And this definition is little bit very difficult to understand under this continuous time representation. However, for the discrete time representation, it is very easy to understand. The discrete time representation, the concept is very easy. It is defined like this: delta n is equal to 1 for n is equal to 0, and this is 0 otherwise. This is very easy. Because in the discrete domain, you have the time value discretized. N is equal to 0, n is equal to 1, n is equal to 2, n is equal to 3, and so on. Or it is equal to minus 1, minus 2, minus 3, and so on. So at n is equal to 0, you have some value. What is that? That is 1. Or n is equal to 1, 2, 3, 4, this is 0, minus 1, minus 2, minus 3, minus 4, 0. But in the continuous time domain, this is not the case. So the signal is defined for minus to plus infinity. But if the signal, if the time is not equal to 0, the signal will equal to 0. But I cannot define properly what is the value of t is equal to 0. So for that, I have to take a small window of size delta. From minus, so symmetric replacement, minus delta by 2 plus delta by 2. So window size is delta. And there is a pulse whose width is equal to delta, height is equal to 1 by delta, and I am approximating that pulse with a 0 width, and that can be regarded as the delta function or delta. And this delta function is very useful in signal systems. Just make a note right at this moment that you have to use this delta function many a times. This impulse function, this is known as impulse function. Let me write it down. Impulse function. Impulse function. And this function has certain correlation with the physical entities as well. So that's why this impulse function, impulse response, many a times we will deal with this function. So as of now, we have seen the sinusoidal function, cosinusoidal function, then the your exponential function, then other types of functions. But this delta function was a delta signal or impulse signal. It possesses a particular property which is not possessed by any of the signals present in the universe. This is the only one signal which possesses a particular property. I will refer to that property later on. But remember that this signal, delta function, will possess a single property that cannot be possessed by any of the signals available in the universe. The close competitor is the sinusoidal signal. Sinusoidal signal also possesses a particular property, that is that the sinusoidal signal contains a single frequency. Hopefully you know, no? A single frequency, pure tone, only one frequency. Sinusoidal signal will be frequency, because you have written like a sine 2 pi f naught t plus omega naught. So that if naught is the signal frequency there. So we will discuss this in detail when we consider the Fourier series and Fourier transformations thereon. So that sinusoidal signal is a close competitor of this delta function from different perspectives. But delta function is only one function available in the universe which possesses this particular property. I will not refer to that property right at this point, but later on definitely I will refer to this. That is all about the delta function. Let me give you just another 5 minutes. So I will complete within these 5 minutes only. So we have defined what is delta function, and so sometimes you might wonder that why delta function is so important. Why it is important, right? So let me give you. Yeah. Can you tell me? What will be the result of this particular integration? Can you tell me what will be the result of this particular integration? We have defined everything. Delta t minus t0. You know what is t minus t0? Last we have discussed the shifting property. We have shifted the signal for positive direction. We have shifted. That means what? Previously you have the pulse was present at t is equal to 0. Now this time the pulse is located at t is equal to t naught. So you have pulse like this. I have excited this one. This is t naught. This is t naught plus delta by 2. This is t naught minus delta by 2. These two times. This time and this time. And this height is equal to 1 by delta. Right? And you have one signal xt which is defined from say minus to plus infinity. And I am multiplying this one. I am multiplying this x of t with this delta t minus t naught. So remember, this delta t minus t naught is nothing but that particular pulse. Another approximation, delta approaching towards 0. If delta approaches towards 0, if delta, this one approaches towards 0, that means this will be basically the impulse function located at t is equal to t naught. So now if I multiply this one, this pulse of unit area with x of t, where x of t can be any function like this function, you have any function x of t like this. Then what will be the integration? What is the result of this integration? What will be the result? That will be that will basically capture the value of x of t at t is equal to t naught. Because the area is equal to unity. We capture that area. So this will give you delta t minus t naught x of t dt. This will give you basically x of t naught. That is known as the shifting property of the delta function. Dirac delta. This is also known as Dirac delta function. Shifting property of the delta function. So if you have a delta function shifted by some amount t naught, might be positive or negative, and if you multiply this with another signal xt which is defined from minus to plus infinity, then this delta function basically it can extract the signal amplitude at that particular time. X of it can be positive as well as negative because we have integrated from minus to plus. Here I have assumed that t naught is a positive, so that's why the signal is shifted in the positive direction, in this direction only. If t naught is negative, then the signal will be in this direction, backward direction. Okay. So if you have a delta function, and if you integrate the delta function, that will give you what? If you integrate the delta function, 1. That means what? 1 means what? This is the step function. So if you have delta function, if you integrate the delta, you will be getting step. If you have step function, if you integrate the step function, you will be getting ramp function. Right? Similarly, you have ramp function, if you differentiate this, you will be getting the step function. If you differentiate step function, you will be getting the delta. Okay. Okay, so these are the different types of signals that we have considered so far. Typically, exponential signal, sinusoidal signal. So you know that sinusoidal signal can be regarded as a component of the complex exponential signal. If you have the complex exponential signal, then this x coordinate, the y coordinate will give you the cosinusoidal part as well as the sinusoidal part. I'm very phasor over there. And then some typical functions like step function. Then we have ramp function and obviously the delta function. So these are the basic functions with which we deal in the next few classes. Okay. So with this, let me conclude the unit 1. Obviously, we have completed the unit 1. The first unit, let me once again refer back what was there. Unit number 1. We have the basics of signals, the notion of signals, classification of signals, continuous, discrete, periodic, aperiodic, energy, power, deterministic, random. That we have discussed. And some basic signals like impulse, step, ramp, exponential that we have discussed, and basic operations of signals like shifting, scaling, reversal, addition, multiplication. Only 2 parts is left, coordination and convolution, that we will discuss in the next class.